Hello, everybody. In this notebook, we are going to learn about image classification using pre-trained models. Now, in the previous notebook, we learned about how to classify 10 different kinds of monkeys. Given a picture of a monkey, we wanted to assign a label to it among the 10 categories, right? But 10 is a small number. What if we want to solve a big problem, something like 1,000 different classes, right? And that brings us to the data set called ImageNet. ImageNet is a data set that was released in the year 2009, and then there was a competition released in the year 2010. This data set is largely due to the efforts of a researcher, Dr. Fei-Fei Li from Stanford University. And she literally put her career on the line because creating a large data set, nobody thought that this would be, this is a good idea for somebody who was looking for a tenure. She was not a tenured faculty at that point. And a lot of people, in fact, some of the luminaries in this field told her that it's a very bad idea to create a large data set because you don't get credit for creating just a large data set, right? But to her credit, she thought that major problems in computer vision would be solved if you actually have a very large data set. So because of her effort and her colleagues' effort at Stanford University, they were able to create this very large data set of called ImageNet. And in 2010, this new competition was released. It was called the ImageNet Large Scale Visual Recognition Challenge, where there were 1,000 different classes. And for the first time, they had 1 million different images for these 1,000 classes, right? So earlier, just to give you a sense of the size of the data sets before this data set was released, computer vision data sets used to be something like 100 different classes, and the total data set size would be a few tens of thousands, and that was considered very big. Caltech 101 was the data set which was the biggest data set before ImageNet came into being, and that actually was also created by Fei-Fei Li. In fact, when she was asked to create this data set by her advisor, Pietro Perona, Perona asked her to create the data set of 100 classes. And she said that initially she was not very interested in creating this data set, but he kept pushing, and she decided, okay, if I'm going to do this work, I'm going to go beyond what is expected. So she created a data set of 101 different classes. Anyways, so this ImageNet data set was a huge deal in the computer vision community, but they did not recognize it just yet, right? So in 2009, when the data set was released, most people did not even take notice, even though this was such a big moment in history. In 2010, when the competition was released, because the problem is so hard, you cannot, there are 1,000 classes and you have to come up with the right answer given an image. Even if the result is in the top 5, we will consider it as a valid result, right? So let's say your image is that of a cat and your top result is actually a dog, but the second probability is a cat, then it qualifies, right? Even if it is in the top 5, it would qualify. So for this top 5, I think the result, that the team that won the visual recognition challenge, they had an accuracy of about 74% in these top 5 categories, right? So next year, the things improved slightly, and the accuracy was about 76% or so, right? And this, people were thinking that every year some improvements will happen, and the increase in accuracy will go up by 2 or 3% every year. So in 2012, something magical happened, right? There was an entry by Professor Jeffrey Hinton and his student Alex Krzyzewski. They came up with a deep neural network based architecture, right? And the accuracy of this model was about 85% or so, right? This was like an earth-shaking moment. This completely changed the foundation of computer vision and deep learning, which had been relegated, which was being ignored by the computer vision community. it became mainstream in the computer vision community, right? This was a huge moment. And, with 85% accuracy, people just could not believe, because in science, we usually don't have this huge leaps in accuracy or, improvements. We usually go in little steps, right? So after that, I think by 2014, pretty much every winning entry was a deep learning entry. Before 2012, none of the winning entries were deep learning based. And by 2014, 2 years later, every winning entry was deep learning based. By 2015, they had crossed human level accuracy, right? So that's an amazing story about ImageNet large scale visual recognition challenge. And now, there are several other data sets which are even bigger than ImageNet, like MS COCO dataset. But this dataset actually set the ball rolling. It brought about a revolution in computer vision. And we have to thank Dr. Fei-Fei Li for this amazing dataset. There's also a book that she has written. I read that book also. It's about her life journey as somebody who came to the United States with very little going for her, and she ended up becoming one of the top names in AI today. Okay, so that was the story about ImageNet. Now let's see what ImageNet has produced. A lot of researchers, they dove into ImageNet after 2012, and they started improving and bringing up new models, right? So the very first model was named AlexNet after one of the authors of the paper. After that, the big companies that started putting in resources, research labs started putting in large resources. So there are a lot of models that were trained on this data set. And, some of the popular ones are that we will consider in this notebook. One of them is AlexNet, obviously the original one. Then we have VGG16. This comes from the visual geometry group, and it had 16 layers. And then came ResNet, which was also a huge improvement over the previous methods. And it also came up with some good ideas. ResNet stands for residual networks. And they came up with some very good ideas like, training a residual network, as well as something called skip connections, etc. So all these improvements gradually, they kept adding on top of each other. They started borrowing good ideas from the networks that came before and adding their own twist to it. And gradually these things became exceptionally good, right? So let's go and install some of these and see how you can do image classification using these networks. It is not already installed. We have to install Torch Vision, and then we have the standard imports. Then we download, this download function basically downloads and unzips all the assets. So I'm not going to go over it. It's pretty standard. We have gone over this code before in previous notebooks. So all our code is in this, all the assets that we want, they are in this Dropbox link, and we can download it, unzip it so that it appears in this notebook. Okay. So as I said, that we are going to deal with 3 different models, and you can actually select a large number of models. They are available in Pytorch. So the process we are going to follow is we are going to load a pre-trained model, and we are going to pre-process the image using transform, just like we did before. As we had gone over this before, that when we load an image, the model is not trained on that image itself, right? It is trained on a modified version of the image. So we have to remove the mean, and then we have to subtract the mean, and we have to divide all the pixel values by the standard deviation. And that's the value that goes in, and the network is able to assign a label to that image. Okay. So we will pre-process, and then we will go over the forward pass. We will send the image through the network, and then we will decode the prediction based on the class names and the class IDs. Okay. So if you load the models, right, these models that are available in Torch Vision, you will see there are a bunch of models available. The first one is called AlexNet. Then we have ConvNext. EfficientNet is modeled by Google. DenseNet. So there are a ton of options. Then we have GooglyNet. This was paying tribute to one of the big names in computer vision, Dr. Jan LeCun, and the Lee comes from his name. So even though it looks like GoogleNet, but the right way to pronounce this network is GooglyNet. Okay, so there are a bunch of options available here, and we are going to select, one of the three we can select. So the first step is pre-processing, right? So we have to define a transform, just like we did in the previous notebook. The transform, what do we do in this? When we load the image, we make sure that it is resized to 256 first. And from that, we take a center crop of 224, because as you know, that all these models after AlexNet, they usually take 224 by 224 by 3 as the image size, okay? Then we convert it to tensor. As I had mentioned, that tensor is basically a multidimensional matrix, and it also converts it to the Pytorch data type, right? And then we have to do this normalization, and the normalization needs two things: the mean, and this we already know what is the mean. This is widely known. What is the mean of ImageNet dataset, and what is the standard deviation? So this is the standard deviation. We will subtract the mean and divide the standard deviation, and that is what is happening in this piece, okay? So all these transforms, they get applied as soon as the image is loaded, okay? Now, we also want the ImageNet class names. So you can go to this and you can see these are the different class names available in ImageNet, right? There are 1,000 of these. Okay, so now we are going to use the ResNet 18 model. The code also shows you how to use different kinds of the other models. So in the models, right, we can load ResNet 18. This is from Torch Vision, right? So we can use, ResNet 18 by calling this function. It says weights equals torchvision.model.resnet18 weights dot, ImageNet 1K underscore V1. Doesn't matter. That's the, that's how you get ResNet 18. And then if you want to get AlexNet or VGGNet, you can just call using these and you can get the default weights from the model. Now, when people trained these models, they can have different weights associated with them, right? ResNet 18 architecture could be trained by different people, and they would have slightly different weights, right? Based on what training parameters they used. So if you want a specific ResNet 18 weight, you can specify it, or you could just use a default weight, okay? So now the model is loaded, and we are going to put the model in evaluation mode. Like I said before in the previous notebook, that there are two modes for running the model. One is in train mode, the other is in evaluation mode. When we are just using it for inference, that is, we are trying to make a prediction on a single image and not training, then we have to put it in evaluation mode. And then we are printing the model here. It just shows you, what is the model architecture. And some of these things will be familiar to you. We have a convolutional layer. We have a batch normalization layer. We have, ReLU activation, and then we have max pooling. And then we have, a whole bunch of other layers. You can go over them. But the main thing is that, okay, the model is loaded nicely, and then we load an image, right? So we are using image.open to load an image, and this is how we display the image, right? Using matplotlib. Once we have displayed the image, we also want to transform the image. So we have the transformed version of the image. Again, remember, in transformation, we are first resizing the image to 256 by 256, and then we are taking a center crop of 224 by 224. And then we are going to remember that in Torch, when you use Pytorch, the data format is different for Pytorch. We have to have a batch, one dimension for batch. We have to have one dimension for channel, which comes first, not last, right? So we need to do this unsqueeze so that our image is transformed into the format that that Pytorch likes. Okay, and to run any model, we can simply pass that image to the model, and we will get an output. And if you look at the shape of the output, right, it will say it is 1,000 long vector, because there are 1,000 classes in ImageNet. We have this 1,000 vector, and the kinds of classes we have already seen in the text file, the classes, but you can see these kinds of, there are mammals, there are carnivores, canines, a lot of dogs in ImageNet, and then we have different kinds of vessels. So it's a very large data set of 1,000 different classes. Okay. Now in these lines, we are loading the labels for ImageNet, right? I had shown you the text file, which is right here. There, basically, this is a comma separated file, and you basically get these the first class is tench, and this is a synonym. So every line has a class and other synonyms. So goldfish, this is the same as the scientific name of the goldfish. Similarly, you can see similar easier ones like bald eagle is also called American eagle, and there are other names, right? So every line corresponds to one class. Okay. So here we are going to read only, we are going to read the lines, so we get all the classes, and then we basically sort the classes, right? Once we get the output, we sort all the classes in descending order, because we are interested in only the top one. And then if you look at that image, right, and we are looking at the top 5 classes here, we made sure that we are just going to look at which are the top 5 classes corresponding to this image, right? The model ran on this image and it produced a vector which was 1,000 long. We sorted the vector based on based on the magnitude or the value inside it. And it turns out that baseball had the highest magnitude, right? So the cell that corresponds to baseball, that had the highest magnitude. And then we also have this baseball player is another one, right? So both of them are pretty high compared to others, right? So the top 2 are baseball and baseball player, right? And the other ones, they are pretty low. Okay. So here we have some code that helps us visualize the predictions, and we have seen this visualization code before, so I'm not going to go over this, but essentially what it does is it displays the image and puts in what was the top ranking class, as well as the confidence of the class, right? The value of the class. So it's 69% sure that it is a baseball, which is true. It is also a baseball player, and that's why it has 30% for baseball player. Now, to make prediction using a pre-trained model, right? This is the simple function, right? What we do is first we put the model in evaluation mode. We open the image, we transform the image and squeeze it, right? Just so that the dimensions are right. And then we put the image, we get the output by doing a forward pass on the model. This is what the forward pass looks like. Once we get the output is going to be a large vector of 1,000 entries. We are going to sort it in descending order so that the biggest entry is on the top, and then we can look at the top entry only, right? If you don't want to look at top 5, we can just look at the top entry, and that is it, right? It will give us which class it belongs to, and we can return the prediction, the image, the class name, and the confidence, right? The class name we are getting by the index of the top class. So here we are just printing that out, and you can pass as many images as you want. For example, this image gives an answer of 98.5% sure that it is a magnetic compass. Ice bear or polar bear. So I'm pretty certain that polar bear is one option for that polar bear class is ice bear. And we can do a search here. Why does it call it ice bear? Because it is in this class, right? All of these are synonyms. So ice bear, polar bear, Ursa, meritimus, whatever it is, right? They all mean polar bear. And it just picks the first one. We are just picking the first one from the list. And that is why it shows ice bear. Okay. Yeah, so that is it. So we learned how to use a pre-trained model that has been trained by somebody else, load it into PyTorch, load the image, and do a forward pass on the image. And then we get the output, and we can display the output on the image itself. So that's all for this notebook. In the next notebook, we will learn how to fine-tune these pre-trained models. So because these pre-trained models are trained on a very large data set, millions of images, if you want to do it yourself, right, it is going to take a long time. So there are a lot of benefits if you can actually take this model, right? It has been trained on millions of images. Even though your problem may be slightly different, you may be solving a different classification problem. If you take these pre-trained models and do something called fine-tuning, you will be able to solve your problem. So you don't have to train a network from scratch. You take this pre-trained model, fine-tune it. It will still require, a few hours sometimes to train the model, but it's not going to take weeks. Like these people must have spent weeks to create the pre-trained model. But by fine-tuning the pre-trained model, you can solve your own classification problem, and that we are going to see in the next notebook. With that, thank you so much.